Yeah, let's do it. So we're going to look at some examples. We're still really talking about estimating area, talking about area under a curve, stuff like that, and kind of having an idea of what this stuff really means. And I have lots of papers here that I want to have accessible to me. So let's take a look at this example here. So we're estimating the area under the graph. By reading values from the given graph of f, use 4 rectangles to find a lower estimate and an upper estimate for the area under the given graph of f from x equals 0 to x equals 8. In each case, we're going to sketch the rectangles that we use. So let's have this left one be the upper estimate and the right one be the lower estimate. So first of all, we have x equals 0 to x equals 8. We want to divide this up into 4 rectangles. So our delta x is going to be 8 minus 0 divided by 4, which is 2. Sorry, one sec. So each of the rectangles we're going to draw is going to have a base of 2. So there's our delta x, there's our delta x, there's our delta x, there's our delta x. Since this function happens to be increasing, we know that the right endpoint is going to give us the overestimate or the upper estimate. So if we're finding the upper estimate, we're going to use the endpoint of 2 and 4 and 6 and 8 to draw a rectangle. So here's my first rectangle. There's the area underneath it. I don't really need to shade in the area. Here's my second rectangle, getting the height when I plug in 4 for x. That looks very nice. It looks like there's a very nice height of 5. Here's my third rectangle right there. And here's my fourth rectangle right here. So we're estimating, right? It doesn't have to be perfect. I'm going to call that value there. Let's see. This is 2. This is 3. This is between 3 and 4. Yeah, it looks a little higher than halfway, but like, let's just call it 3.5. So the upper estimate here, I'm going to call that, yeah, they did say upper. So I'm going to say U4, my upper estimate using 4 rectangles. You could also call it R4 because we are using right endpoints to estimate it. It doesn't really matter what you call it, but like, try to be appropriate here. So for my first rectangle, my base is 2, my height is about 3.5. For my second rectangle, my base is 2, my height is exactly 5, or close enough to exactly 5, I'm going to say 5. For my third rectangle, my height, yeah, I would feel maybe slightly guilty about saying that's 5.5, but not that guilty. And my last rectangle, my height appears to be 6. So that's not too bad. That's going to be, now I will point out, I probably could have factored out the 2. It might have made it easier, probably would have made it easier, but it's also not that big a deal. 2 times 3.5 is 7. 2 times 5 is 10. 2 times 5.5 is 11. 2 times 6 is 12. So it looks like we're getting 7 plus 10 plus 11 plus 12, which is what? 40? So that's our estimate for the area under this curve, using upper estimates, clearly an overestimate. Same picture. Now we're going to use what's the word here? Sorry. A lower estimate, not an underestimate. So a lower estimate, again, same intervals from 0 to 2, from 2 to 4, and from 4 to 6. But now each rectangle, we're going to use the left-hand endpoint because that's going to be the endpoint that's going to give us the lower function value. So there's our first rectangle. And for the next one, between 2 and 4, we're going to use 2. We're going to find the height at 2. There's our rectangle there. It's going to be pretty much all the same values we had before, except for one difference. From 4 to 6, we're using 4. We're getting the height there. And finally, from 6 to 8, we're plugging in 6 to get the height there. So here's our lower sum, or our underestimates, or our left endpoints. So left and lower both start with L. How nice is that? So our left endpoint using our left endpoints using 4 rectangles, or our lower estimates using 4 rectangles, we're going to get, here I am going to factor out the 2. So my base is 2 for every rectangle. This first rectangle has a height of 2. The second rectangle has a height of about 3.5. Again, probably not a very good estimate. My third rectangle has a height of 5. And my fourth rectangle, I said it was 5.5 before. I'm going to say it again, even though I feel like it's a little not perfect. That's okay. Here, adding these up together, we get 2 times let's see, 5.5 plus 3.5 is going to be 9, plus 5 plus 2 is going to be 16. So 2 times 16 is 32. And that's going to be obviously an underestimate. So when you're asked to estimate things, you really just, it is an estimate, right? It does not have to be the perfect right amount of area or the perfect height of your rectangle, just to be close. Not even that close, really. Let's see, what else? Sure, we could do one more. Yeah, let's look at this. So we got two more, another example that's kind of different in nature. So let's look at, I should slow down for a second. Let me pause. Any questions about this? Left endpoint. So I will say we could have also been asked to use the midpoints to estimate it, right? I don't have in fact, why don't I do that? Ha ha ha. Instead of doing what this next one says, using 8 rectangles, which I really don't want to do, we're going to use midpoints instead. So we're still going to use 4 rectangles, but now using midpoints. Wow, that looks terrible. So between 0 and 2, the midpoint is 1. We're going to plug in 1 to find the height. There's our rectangle, which seems to have a height of exactly 3. How nice. Between 2 and 4, we're going to use the input of 3 to find an output of, that looks like about 4.5. Similarly, between 4 and 6, we're going to use the midpoint of 5. That looks like, I feel like it'd be kind of wrong to call that 5.5. We'll give ourselves an estimate here a second. Finally, plugging in 7, we get that height there, which you can see is not quite fully 6. A little off. So I'll try to be slightly more precise with my estimates this time, just to kind of point out that you can be. So here, the area under the curve is going to be approximately, well, we're using midpoints with 4 subintervals. My base is 2 in each case. The height of this first rectangle is 3. The height of the second rectangle, I'm going to say is like 4.5. I feel like these could be better labeled over here. I said what, 4.5? Yeah, that seems plausible. The next one, okay, it's not quite halfway up. Let's call it 5.4 just to be pretending like we're being more precise. And then the last one here is 7, and you plug in 7, you're getting almost 6, but you're like not quite there. Let's say it's 5.9. I'm just making things up, really. I mean, I'm like making things up that make sense, but I'm really like just using my eyeballs and be okay, well, sure, close. Here, if we add these together, yeah, I made the math a little harder on myself, so I actually have to add these things together. 5.4 plus 5.9 is what? 10 plus 1.3, 11.3. Those add up to 7.5. Add those together, you're getting 18.8. You're getting 2 times 18.8, which is going to be 18.8 times 2. Here's what I would do. I know that 18 times 2 is 36. I know that 0.8 times 2 is 1.6. And then add those together, you get 37.6. Thanks. If you didn't get your name on this, I'll leave it up here. You can put your name on it. So, cool. It's not too bad. Estimating is usually not too bad. Well, I should say estimating with a graph is not too bad. Let's look at a different kind of estimation thing where it's a similar-ish idea, but you're given different information, kind of. I think this is one of the homework problems for the people who have web work, or similar to it anyway. So let's see what the problem says. The table shows the number of people per day who died, how light, who died from SARS in Singapore at 2-week intervals beginning on March 1st, 2003. So this is deaths per day, and this is the date. We want to estimate the number of people who died of SARS in Singapore between March 1st and May 24th using both left endpoints and right endpoints. Okay, so we're going to estimate the number of people that died in the first 2 weeks to start off with. So first 2 weeks, and we'll do it first using left endpoint. So this is using left. So in left is kind of maybe not the right word to use here. If we're talking about time, left is referring to like the earlier time, right is referring to the later time. So in this first interval from March 1st to March 15th, the left endpoint is March 1st that we're going to plug in to the function and get the output value of 0.0079 deaths per day. So in the first 2 weeks, we're going to have 0.0079 deaths per day multiplied by the number of days in that interval, which is 14 days. And then we're going to do the same thing for the next 1, 2, 3, 4, 5 intervals, right? There's 6 intervals altogether from March 1st to 15th, from the 15th to the 29th, from the 12th to the 26th, from the 26th to the 10th of May, and from the 10th of May to the 24th of May, right? 1, 2, 3. Oh, did I say 6? I missed one in my markings here, sorry. From the 29th to the 12th, and then the 12th to the 26th. Yeah, there's 1, 2, 3, 4, 5, 6 intervals, meaning we should be adding up 6 things, not 7. So it's going to look the same, right? The second 2-week interval is going to be, we're using the left endpoint, so it's going to be 0.0638 times 14. I don't think we need to write all this thing every time. So essentially, using left endpoints, our estimate for the total number of deaths is going to be all of the first 1, 2, 3, 4, 5, 6 deaths per day values multiplied by 14. So it's going to be 0.0079 plus 0.0638 plus 0.1944 plus 0.4435 plus 0.5620 plus 0.4630 multiplied by 14. I don't see a lot of value in actually doing that calculation, right? You can add that up or not, and then multiply by 14. Specifically, if you're working with web work, well, actually, I'll get to this point in a second. In a similar way, if we do it using right endpoints, it's going to be practically the same calculation, except now we're going to, instead of using the 0.0079 for the first subinterval, it's going to be the 0.0638, and then the 0.1944, and then this one, and then this one, and then this one, and this one. So usually if you're using left endpoints, using all the endpoints except for the last one. Sorry, all the endpoints except for the last one. If you're using right endpoints, you're using all the endpoints except for the beginning one. So here, using right, it's going to be a pain to write out again, but we'll do it. 0.0638 plus 0.1944 plus 0.4435 plus 0.5620 plus 0.4630 plus 0.2897, all times 14. Cool. It is good to think about the units on this, just so we kind of make sure we've got the right kind of answer at the end. So I'll point out, whatever this number is here, and it's some gross number, this is the number of deaths per day. And over here, this 14 is the number of days. So when we multiply these two units together, the deaths per day multiplied by days, the days cancel, and you get the number of deaths, which is what we were trying to calculate. It's always good to think about how the units are working out when you're multiplying these things together to see if the thing you're getting really is like the quantity you're trying to get. Let's look at one more example in the same vein. But, oh, this is going to be challenging. Yeah, all right. It'll be fine. It may work. So here is a web work problem that's very similar. Yeah. So let's read through this. So what's it say here? Speedometer readings for a motorcycle at 16-second intervals are given in the table below. So at time 0, the velocity is 90 feet per second. At time 16 seconds, it's 84 feet per second, and so on. After 32 seconds, 77 feet per second. Seems pretty fast. Yeah, 60 miles per hour is 88 feet per second. I guess it's not that fast for a motorcycle, right? It's okay, right? Here you're going a little under 60, here you're going a little over 60. All right, seems okay. And so on. First question is to estimate the total distance traveled by the motorcycle during the entire 80-second time period using the velocities at the beginnings of the time intervals. So just to kind of point out here, to find how far the motorcycle traveled in the first 16-second interval, we're going to take our 16-second time period and multiply it by 90 feet per second. Because, right, we're using, for this first interval, we're using this to estimate kind of the speed the whole time, even though we know it's not the speed the whole time. Paper. So I'm okay. I'm gonna draw a thing real quick. I'm gonna move this back over so you guys can see what I'm doing. Which is why it's kind of a pain, but whatever. So if I were to graph this for a second, we've got something kind of like this. So our times on the x-axis, 0, 16. No, no, 0 starting, not on the terrible fail. Let's try that again. Okay, one more time. Time on the horizontal axis, 0, 16, 32, 48, 64, and 80. And my velocity values, starting as with 90 is the highest. So we've got 90, and then the next one is 84. So I'm just going to kind of freehand it here. So the next one's 84, it's a little bit lower. The next one's 77, a bit lower. Next one's 69, even lower. Then 74, a little bit higher, and then 79, a little bit higher. So there's my values, kind of. And so you might imagine that the velocity of the motorcycle follows some curve like this, right? Not being constant, just, accelerating, decelerating, changing speed. But to estimate how far the motorcycle has traveled, we're going to say, well, for this first interval, if we're using the what did they say? The values at the beginnings of each time interval. Well, for this first time interval from 0 to 16, we're using this value of 90. So we're getting this area, 16 times 90. And for the second one, we're going to use, again, the beginning. So we're going to use that one. So it's going to be whatever, 84 times 16 times 84. And so on. We're always using the beginning one because that's what the instructions told us to do. Some of those are over, some of those are under because this function is neither always increasing or always decreasing, right? I've got some variability here. So 16 times 90, 16 times 84. Let's go back to the thing here because I wanted to show you something that I think is somewhat useful. And I know there's some problems in the first homework assignment that Bert gave you to help you kind of see this. You don't have to calculate this. You can say, oh, sorry, I have to look here. It's not right there. They said they were going to fix this. They haven't fixed it yet. So instead of actually calculating what this is, you can just say it's 16 times 90 plus 84 plus 77 plus 69 plus 74 plus 79. And in a similar way, if we're using the velocities at the end of the time intervals, we could be smart, copy this, paste it, and say, well, we want to use the ends of each time interval. So instead of 90, 84, 77, 69, 74, we wanted to start with 84 and then with 79. So, what did I do? I did too many, right? This is gonna, if I submit this right now, the first one's definitely gonna be wrong, right? The first time interval should be 0 times 9, sorry, 16 times 90. The second one from 16 to 32 is gonna be 16 times 84. And the very last one from 64 to 80 should be 64 times 74. 64 times 74? 16 times 74. The time interval, 16 seconds multiplied by the velocity, 74 feet per second. I don't want that last one there. Apologies. And then for the second one where I'm using the ends of the time intervals, instead of using 90 through 74, I should be using 84 through 79. Notice I'm not actually doing the adding on my own. I'm just going to let WebWork do it for me. And then we... Well, it's right. I promise you it's right. I checked it before and it worked out just fine. Yeah, that's annoying. But it definitely did work and it did come out right when I checked it before. So please believe me that you don't have to do that work. You can just like type it in there like that. It's very nice. Yeah, I forgot about that. Okay, well. Still nice to know because you don't have to actually, right? The point of that problem isn't to add numbers together. You know how to add. The point of the problem is that you understand what they're asking you to do and doing that thing. Why did I use 16? Good question. Of course, I closed the thing here. So the reason I use 16 is because they told us, well, in fact, let's go back to what you did. So they're telling us that they're measuring the velocity of the motorcycle every 16 seconds. So for this first period, this area here is multiplying 16 seconds by 90 feet per second. When you multiply those together, the units of seconds cancel out, and we're left with it's 144, so 1,440 feet. But that's why we use 16 seconds, because this time interval is 16 seconds elapsing. And every time interval in this particular example is 16 seconds, right? This next one is also 16 seconds, and you get 16 times 84, whatever that happens to be. It's going to, sure, 6, yeah, whatever. It's 1,344, I think. I don't know. I don't really care that much. But the point is, that's why we're picking that number, because that's the interval. Just like in the previous examples, right? Whatever the width of our base was, that's what we were multiplying by the height of our rectangle. In this example, which I know you can't see the actual question anymore, right? They're not giving you the picture of the bases and the heights, but that picture still is there. We just don't see it. So back to, sorry, I've got papers all over the place here. Thought I had something else I want to show you. I must have lost it. Sorry, that happens a lot with me, is I misplace papers all the time because I've got so many papers going on. But that's why. All right. So estimating is always fun. I should ask you all, have you been talking in your class about the limit definition of the area under the curve? All right. I figured probably yes, but sometimes people don't cover it, and so I just don't want to sure I didn't want to spend your time doing that before if you didn't have to do it. So let's go ahead and talk about that. Before we talk about that, though, we should talk a little bit more about sigma notation, because that notation does become extremely important in this context. So let's look at, hold on, let's start this off here. Sure, we'll start here. So here's some sigma notation. It doesn't really matter what index you use here, whether it's a K, an I, or a J. Those are typical choices, but you can use kind of anything really. All that means, all this notation means, is we're adding a bunch of stuff up. That's what the capital sigma means. You're adding a bunch of things up. What things? Whatever this formula is equal to when you plug in K equal to 1, and then add and plug in K equal to 2, and so on and so on. So we can write this as 3 times 1 plus 2, plus, now K is going to be 2. 3 times 2 plus 2, plus 3 times 3 plus 2, plus 3 times 4 plus 2, plus 3 times 5 plus 2. And that's the end of the story, right? Here's where K is equal to 1, K is equal to 2, K is equal to 3, K is equal to 4, K is equal to 5. And we can figure out what this is, right? This is going to be, geez, do I really want to? Yes, I really do. 3 plus 2, 5 plus 6 plus 2 is 8 plus, I know it's going to be 11 plus 14 plus 17, which is going to be 13 plus 11 is 24, plus 14 is 38, plus 17 is 40, 55. Not really the point, though. Most of the time, actually finding the value is not really the point. There is another point I do want you to see, though. Instead of finding out what this adds up to, I want to show you something else here. So look at this expression I've got here. I'm going to break this up into 2 distinct pieces. I'm going to put the 3 times a thing first. Say, cool, I have 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. And then I also have the 2 plus 2 plus 2 plus 2 plus 2. Or writing it in a somewhat different summation or sigma notation, I can write this as, let me do one more. Let me break it this way. I'm going to write this as 3 times 1 plus 2 plus 3 plus 4 plus 5, plus 2 times 1 plus 1 plus 1 plus 1 plus 1, 5 times. And then I'm going to rewrite that as 3 times the sum from K equals 1 to 5 of just K, plus 2 times the sum from K equals 1 to 5 of just 1. So what we're seeing here is 2 things at once. One, if you have a summation of things that are added or subtracted together, you can break that apart into two summations that are added or subtracted together. And any constant multiples you can pull out in front of the summation, right? Adding up 3 times 1 plus 3 times 2 3 times 3 plus 3 times 4 plus 3 times 5 is the same as adding up 1 plus 2 plus 3 plus 4 plus 5 and then multiplying it all by 3. So when you have a constant multiple like 3 times k, and you're taking the sum of that, you can rewrite it as 3 times the sum of k. Similarly, here it's not as necessary to pull out this 2 because you're still off to the one side. But if you're adding up a bunch of the same number however many times, you can always pull out that constant and be left with just a 1 inside. And when you add up 1 5 times, what do you get? 5. When you add up any constant some number of times, you get that constant multiplied by that number. So what I really want to point out here is something more general. Let me get some actual paper here. Everything everywhere. So some summation things to know. Let's go down here. Summation / sigma rules. So 2 rules in one, but we'll write them separately. First thing, if you have the sum from k equals 1 to wherever, n, of some function of k plus or minus some other function of k, or some sequence that depends on k. I said function, but we really mean sequence. You can break that up as the summation from k equals 1 to n of the first part, plus or minus the summation from k equals 1 to n of the second part. And again, what's really happening here, right, just to show it, this first part, if you write it out, well, if I plug in k equals 1, I get a sub 1 plus or minus b sub 1. If I plug in k equals 2, I get a sub 2 plus or minus b sub 2. All the way to the last nth term, I get a sub n plus or minus b sub n. But then we can break that apart into just the a's and just the b's. So this is a sub 1 plus a sub 2 plus all the a's all the way to a sub n. And then we have plus or minus b sub 1 plus or minus b sub 2 all the way to plus or minus b sub n. But again, we can just rewrite that as the sum from k equals 1 to n of a sub k plus or minus the sum from k equals 1 to n of b sub k. So it really is true when you have the summation of things added or subtracted together, you can break it up into summations added or subtracted together, which is useful when we start trying to do this limit definition stuff. Similarly, the other thing I wanted to say was that if you have the sum from k equals 1 to n of some constant multiplied by your thing that depends on k, a sub k, that's going to be equal to that constant multiplied by the sum from k equals 1 to n of a sub k. And I think you all could probably see it. If I write this one out, I'm going to have c times a sub 1 plus c times a sub 2 plus c times a sub 3 all the way to c times a sub n. If I write this one out, it's going to be c times a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n. And I think we can agree those are the same, right? This one just has the c factored out. This one doesn't. Okay, let's look back at the summation notation stuff because there's a little more to see here. So this next one, really the same idea. We're just plugging in things and calculating things. If you wanted to, though, you could break this apart, right? We could rewrite this first as the sum from k equals 2 to 4 of k squared plus 5 times the sum from k equals 2 to 4 of k minus, I like to leave the 3 inside personally, the sum from k equals 2 to 4 of 3. And now we're going to calculate it. So starting here, if I plug in 2, I'm going to get 2 squared plus then 3 squared plus then 4 squared. That's the first summation. For the next part, I have plus 5 times the sum from k equals 2 to 4 of just k. So that's going to be 2 plus 3 plus 4. Finally, I feel like people sometimes struggle with this last one. I have the sum from k equals 2 to 4 of 3. Here, it's a little easier to see, I think, because you're substituting in the value of k each time. Like you're plugging that k value in somewhere. Here, there's nowhere to plug it in. So when k equals 2, I'm going to add a 3. When k equals 3, I'm going to add another 3. When k equals 4, I'm going to add another 3. That's what's happening when you're taking the sum of as a constant. You just keep adding that constant however many times there are that many terms. If you're starting at k equals 2 and ending at k equals 4, that's 3 terms. 2, 3, 4. If you want to find out how many terms you've got, you take the end term, subtract the beginning term, and then you add 4 minus 2 is 2, 2 plus 1 is 3. That's how many terms you've got, because you're like off by 1 because of counting. Then you could add this up. This feels like the not important part. 4 plus 9 plus 16 plus 5 times 9 minus 9. That's going to be 29 plus 45 minus 9. Something. 45 plus 20, 65. Cool. Again, not the important part. And then sometimes it's useful to be able to go back and forth, to start with a summation and expand it out as a bunch of stuff, or to start with a bunch of stuff added together and write it as a summation, which is probably the harder part, actually. So let's see here. I've got all these terms, 7 plus 12 plus 17 plus 20. Okay. When you're trying to figure out how to write something in sigma notation, you want to kind of look for a pattern. The pattern I am seeing here, and often to see the pattern, I look at like the differences between terms. So here, I'm noting that each next term is just 5 added to the previous term. So that means I probably need something like 5 times k. So if I did the sum, yeah, let's just write it this way. So if I said my a sub k was 5 times k, that wouldn't be quite correct. So if k is 1, I'm going to get 5. If k is 2, I'm going to get 10. If k is 3, I'm going to get 15, and so on and so on and so on. So what I'm really going to do is I'm just going to plug in k equal 1 and then ask myself, how much do I need to add on to get what I need to start with? Well, plugging k equal to 1, I get 5. I want to start at 7, so I have to add exactly. So that's what I'm going to be adding the terms up for. My a sub k that's going to be in my summation is going to be 5k plus 2. So I'm going to start, I'm going to write the sum. I do want to start at k equals 1. You don't have to start at k equals 1 in general, but it's usually an easy place to start. And then my thing I'm adding up is 5k plus 2. You don't really need parentheses there, but I like them. Now, the question is, where do we end? Well, there's 2 ways to figure this out. You could either set 5k plus 2 equal to your last term, and then solve for k. Subtract 2, 5k equals 40, divide by 5, k equals 40 over 5, which is 8. Or you can count the number of terms. 1, 2, 3, 4, 5, 6, 7, 8. Either way, you're going from k equals 1 to 8. That is an advantage of starting at k equals 1, is if you start at k equals 1, the number of terms will be the superscript here that you end at. This one has an asterisk. That means it's probably harder. Let's take a look. And again, I should remind you all, we're welcome to ask questions at any time. I know I talk kind of fast, only when I'm teaching, really. But if you have questions, don't hesitate to ask us something. I'll try to slow myself down by drinking some water here. Yeah.
Get that from.
So the plus 2 here. So I got it by first saying, I know that if I'm increasing by 5 every time, I need a 5 times k. Because how much is k increased by every time? Not generally. In general, k increases by 1. Right? We start at k equals 1, and then k equals 2, and then 3, and then 4, and then so on. Right? It's always, always, always your k is called the index, or whatever that letter is down below the summation. The index always increases by 1 every time. But if we have something that's increasing by 1 every time, and we want our function to increase by 5 every time, the thing that's increasing by 1 gets multiplied by 5. That's why we have a 5k here. The problem is, if we just had 5k, if k equals 1, you get 5. If k equals 2, you get 10. But we want, when k equals 1, to get 7. And when k equals 2, to get 12. And we can see that the difference between each of our terms and the terms we want is 2. So we just added on the 2. Here, I'm still going to look at the differences. I see a 5, I see a 7, I see a 9, I see an 11, I see a common pattern. If I look at the differences of the differences, I see a constant thing. So Let me ask you guys a totally different question. What's the derivative of 5x? Right. So I would say that we're changing by 5 every time. Our derivative is 5. So our function is kind of like 5x or 5k. The derivative of 5x plus 2 is also 5, or 5k plus 2 if k is a variable is also 5. Here, the derivative isn't 2 because it's not the change that's 2, it's the change of the change. Kind of like the second derivative. It's kind of like your second derivative is 2. The antiderivative of 2 is 2x. The antiderivative of 2x is x squared. It's kind of like our function is x squared. And fun fact, the common pattern I was talking about that I said to myself is that when you're increasing by the next odd number every time, that's a very key sign that your pattern has a square in it. So this is something like k squared, but not quite, because is it 5? That's not a square number. 10 is not a square number. But I know because of experience that when you have odd numbers like this, where the difference of the difference is all 2's, you have something squared. So there's a couple ways to do it. Well, let's see. All those numbers look like they're off a square number by just 1. 5 is really 4 plus 1. 10 is really 9 plus 1. 17 is 16 plus 1. 26 is 25 plus 1. 37 is 36 plus 1. So I could think of this now. I think there's two really, really valid ways of writing this. You could either do this as the sum from k equals 2 of k squared plus 1, because if you start at 2, 2 squared plus 1 is 5. And then the next one is 3 squared plus 1 is 10. The next one is 4 squared plus 1 is 17. And then you're going to end at k equal to 6. As we can see that the last term is 6 squared plus 1, which is 36. It's 37. Also, from 2 to 6, how many terms do I get? 6 minus 2 is 4. Oh, 5. 1, 2, 3, 4, 5. We're good to go. Or also perfectly acceptable, you could start anywhere you want, really. So you could start at, say, you could go from k equals 1 to 5, but then you have to be a little bit more careful. I don't like this as much, but you could totally do it as k plus 1 squared plus 1. Essentially, we started 1 back, so we had to scooch everything 1 forward to make up for it. Right? We started at a lower value of k, so we said, well, this needs to be bigger so that we still end up with the same thing. Plug in k equals 1, you get 2 squared plus 1. Just like here, when you plug in 2, you get 2 squared plus 1. Either of these is acceptable. This is not that important because we don't do a whole lot with summation notation in this class, but I will say the slightly unfortunate answer here is that there's technically like an infinite number of ways you could write any summation. Usually there's a few that there's like 2 or 3 that are usually like we're looking for, but there's technically a lot of ways you could do it.
How did you know to pick k equals 2?
Because that's a good question. Because I saw this as 2 squared plus 1, and this as 3 squared plus 1, and this as 4 squared plus 1. So usually when I'm trying to find like the pattern for the thing, I'm looking for a thing that is increasing by 1 every time, right? So it's not that, right, it was the thing getting squared that is increasing by 1. So I knew I wanted to start with something there, and then it's going to increase by 1 every time. And since I am seeing this starting not at 1 squared plus 1, but at 2 squared plus 1, I'm picking k equal to 2 to start with. Yeah, let's see. What else do I have? More of that. Okay, sure. How much time have we got here? Not a whole lot. Okay. So I think Friday we'll finally get to say something about the limit definition stuff, but there's a couple more summation notation things we need. Yeah, let's talk about this. So there's 2 more really important formulas, which I think are okay. There's one I'm going to prove to you, but there's a few others. So we did mention, I'm going to say it again, the sum from k equals 1 to n of just a constant is just that constant multiplied by n. Or however many terms you get. So I'm just going to add on. No, that's not important. I don't need to say things that aren't that important. But here is a more interesting formula. The sum from k equals 1 to n of k, which is 1 plus 2 plus 3 plus 4 plus all the way to k minus 1 plus k. So, n minus 1 plus n. Holy smokes. Terrible. We're ending at n, not at k. K is the thing that's changing every time. Okay, there's a formula for this. And it's one you're probably expected to memorize. You might be expected. I don't know. Maybe you are, maybe you aren't. But the formula for this is n times n plus 1 divided by 2. And you may be like, well, where did that come from? Well, for this one, there's actually a really kind of slick way of proving it. It's not true for the other ones, but I do want to show you this because I think it's neat and just kind of neat to see how like math can be cool sometimes. So cool depending on your definition of cool, you know. So how do we know that this thing, the sum from k equals 1 to n, which is 1 plus 2 plus 3 plus all the way to n, how am I going to get that formula? Well, here's what we're going to do. We're going to add it again. So we're going to add this summation. Oh, there's a k there. Sorry about that. We're going to add the summation to itself. But this time when I write it, I'm going to write it in reverse order. So instead of 1 plus 2 plus 3 plus all the way to n, I'm going to write it as n plus n minus 1 plus n minus 2 plus all the way to 1. Still the same numbers. Doesn't matter what order you add things up together in. Things add together in the same way, regardless of the order. Not true for subtraction. But now we're going to add these vertically. So on the left side of my equality here, I have the sum from k equals 1 to n of k plus the sum of k equals 1 to n of k. If you add something to itself, you're just doubling it. So that's 2 times the sum from k equals 1 to n of k. On the right side, here's where the fun happens. So I'm going to add vertically. 1 plus n is n plus 1, or 1 plus n. 2 plus n minus 1 is how much? It's also n plus 1. How about 3 plus n minus 2? Also n plus 1. All the way to the very last term, which is n plus 1. Okay, important question. How many n plus 1s did we add together? How many terms are there that I've written out here? And I know I didn't write all of them, but there's 1, 2, 3, all the way to n terms. So if you add up n copies of a thing, that's really n multiplied by that thing. So we can write this as 2 times the summation from k equals 1 to n of k is equal to, well, this is occurring n times. So it's really going to be n times n plus 1. And then to finish it off, we divide both sides by 2. Sum from k equals 1 to n of k is n times n plus 1 divided by 2. Pretty cool. Now, there are 1 or 2 other formulas that you might be expected to know, and there is not such a slick proof for them. I'll go back over here to write them down. I'm trying not to cover things up here too much. Yeah, not going to work. I'll just have to cover it up. Here's the other 2 formulas that you might be expected to know. The sum from k equals 1 to n of k squared, which is going to be 1 squared plus 2 squared plus 3 squared plus all the way to n squared. It's n times n plus 1 times 2n plus 1 divided by 6. Sorry, it's kind of low. Apologies. And finally, what time is it? Oh, we got. And lastly, the sum from k equals 1 to n of k cubed. This one is also really neat. So you get 1 cubed plus 2 cubed plus 3 cubed plus all the way to n cubed. Now here's something that's kind of cool about this formula. Papers. That's why I do it the other way usually. That's going to be n times n plus 1 over 2 squared. This is just something I think, maybe not just me, other people probably think too, but there's something really neat here that I think is cool. If you add up the first n numbers and then square it, it's the same as adding up the cubes of the first n numbers. Let me show you what I mean. Just because, again, I think this is worthwhile. It might not be that worthwhile, but that's the joy of teaching a class. You can show people things you think are cool. So check this out. 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed is equal to 1 plus 8 plus 27 plus 64, which is 9 plus 27 is 36 plus 64 is 100. You know what else is 100? Lots of things, but specifically 1 plus 2 plus 3 plus 4 squared. And that's true regardless of where you end. What I mean by this is you could say this, you could say 1 cubed plus 2 cubed plus 3 cubed plus pick your ending point. Let's end at 10 cubed. Whatever that adds up to, it is literally the same as 1 plus 2 plus 3 all the way to 10 squared. Not a vital thing to know. I just think it's really cool. So yeah, but it is, but it is vital in that it's how I actually remember that these formulas are what they are, right? The way I remember this last formula I showed you, this formula for the sum of the first n cubes, is I'm like, oh yeah, it's that formula I already used, and you just square it. Kind of nice. Yeah. So next class on Friday, we'll actually talk about using these summation notation formulas to help us actually find the exact area under some curve. How neat. And I have office hours over in the South Silo, and then I have another class.